Section 5. Visualizing the expanding universe, not an explosion. Perhaps the natural way to explain that galaxies are receding from us would be that we are at the center of the universe, that the universe was originally compact at its center, and then the universe exploded out from that center. So the galaxies are moving away from us. That is wrong. Cosmologists have adopted what is called the cosmological principle that, viewed on a sufficiently large scale, the properties of the universe are the same for all observers. If this principle is true, then for any galaxy we might choose, all galaxies distant from it are receding away from it, and the recession speed is roughly proportional to distance from it, with the same proportionality for all observers. The recession of the galaxies is not an explosion away from us or from any spatial center. We are not at the center of the universe. Our location is not unique or special on the scale of the universe. It is believed that whether our universe is spatially infinite or finite but with no edges, the universe has no center at all. The recession of the galaxies is not a finite explosion inside infinite space. So, what is it? It is expansion of the universe. The distance between distant galaxies in our observable universe is increasing with time. We will get to the mathematics of the expansion of the universe, but first we must stop thinking about explosion from a center. So we will start with simplified mental images of what it would be like for space to expand. Let's first see how expansion of the universe works in one spatial dimension, the horizontal axis. Assume it is infinitely long. The vertical axis is increasing time, starting at some time with some spacing. Look at the bottom row, earlier in time. Let's imagine each colored circle to be a galaxy cluster, but we will call it an observer. Each galaxy cluster is a gravitationally bound group of galaxies, such as our local group, of which the Milky Way and Andromeda are the largest galaxies. Galaxy clusters are smaller than and different than superclusters, which experience gravitational attraction but are not gravitationally bound, such as our Virgo supercluster. For simple visualization, we will take all observers' galaxy clusters to be equally spaced from their two nearest neighbors at all times. And we will let that universal spacing increase with time upward along the time axis. Here we show 7 observers, and initially we will be the observer shown in red. We can only see horizontally, that is our entire universe for the moment. We see all other observers moving away from us as time passes. But that's exactly what every observer sees. It is not unique to the red observer. The red observer sees the gold and green observers moving away from itself at the same speed but in opposite directions. The red observer sees the gray and blue observers moving away at the same speed as one another in opposite directions, but at twice the speed as the gold and green observers, because they are twice as far from the red observer. This is Hubble's law. Recession velocity is proportional to distance. Now, change your perspective to a different observer, say the green observer. The green observer sees the red and blue observers moving away from itself at the same speed but in opposite directions. The green observer sees the gold and black observers moving away at the same speed as one another in opposite directions, but at twice the speed as the red and blue observers, because they are twice as far from the green observer. Hubble's law applies for all observers and does not require the universe to have a center or any absolutely stationary point. The motion is all relative. I made the circles large enough for you to see the colors, but you must mentally replace these with very small objects, much smaller than the separation distances. And the size of the objects do not change as the universe expands. Maybe you imagine that the horizontal spatial axis was a string of rubber being stretched from the ends. If so, that's okay for now, but the universe is not being stretched from its ends. It has no ends, whether it is spatially infinite or finite. Now we imagine two spatial dimensions. I think you can imagine a second spatial dimension going in and out of the screen and expanding identically in time. Each observer would confirm the identical Hubble's law in two-dimensional space. If I had better skills, I could show a two-dimensional plane expanding in time as a GIF, but I hope you can imagine it well enough. Imagine a two-dimensional expanding universe that is spatially infinite with no edges. I hope you can also imagine adding the third spatial dimension and the universe expanding in time in all directions. Maybe you imagine that the spatial plane was a finite sheet of rubber being stretched from all its edges. If so, that's okay for now, but the universe is not being stretched from its edges. It has no edges, whether it is spatially infinite or finite. Often the analogy is made to baking raisin bread. As dough, the raisins are closer together. When the bread rises, all the raisins move more distant from one another. I hate this analogy because it is finite, has edges, and suggests the universe must be expanding from one place into another, which is just wrong. A universe can also be finite, but with no edges. Often the two-dimensional analogy is the two-dimensional surface of a perfectly spherical balloon, instead of an infinite plane or rubber sheet. Here I am showing 5 colored dots, five galaxy clusters, 5 observers, whose entire existence is along the surface of the balloon. Light travels along the surface of the balloon only, not through the inside of the balloon. What seems like the inside of the balloon to us in 3 dimensions does not exist in this two-dimensional universe. As time passes, the universe expands. The distance between galaxy clusters increases with time, and the observed recession velocities increase with distance measured in that universe, the balloon surface. The orange observer sees the blue observer here as receding faster than the green observer, which is at closer distance. Each observer would confirm the identical Hubble's law in this two-dimensional space. This surface of a balloon is an example two-dimensional expanding universe that is spatially finite, yet has no ends, no edges, no spatial center within that universe. We can't easily visualize that it is possible to have a three-dimensional expanding universe that is spatially finite, yet has no ends, no edges, no spatial center within that universe. But mathematicians and physicists can handle this. It is not known conclusively whether our three-dimensional expanding universe is spatially infinite or spatially finite, though perhaps huge, yet has no ends, no edges, no spatial center. Here is a different balloon representation showing galaxy clusters in yellow at two different times in the expansion. Imagine each galaxy cluster as a small button or sequin glued to the surface of the balloon. The squiggly lines represent photons, light, traveling through empty space between galaxy clusters. Imagine the squiggly lines as drawn on the surface of the balloon. A very important characteristic of the expansion of the universe is that the wavelengths of photons of light traveling between galaxy clusters, the wavelengths increase directly with the expansion of the universe. This is true for visible light and for gamma rays down to radio waves. Expansion reduces the energy of those photons and decreases the radiation temperature of the universe over time. The universe was extremely hot initially and is now pretty cold due to expansion. The visible light photons are shown as shorter wavelength and blue on the left, and longer wavelength and red in color on the expanded universe on the right. This is called cosmological redshift due to the expansion of the universe. More on this later. Here is another view. Before I start the animation, here is one galaxy, here is another galaxy. The galaxy on the right has emitted light, which is a sine wave here. I know you can't see it very well yet, but it's a sine wave traveling to the left through the universe, and we're going to see that its wavelength expands as it travels. It's traveling, it's expanding, it's expanding, it's expanding. This is the end of section 5.